Okay, as everyone is joining, we'll get ready to kick things off here. We've got a lot of content to cover. This is the Interface Force Leaders webinar, Decoding Sensor and Instrumentation Communication Protocols. Quite a mouthful. Our guest presenter and expert is our own Keith Skidmore. He is what I like to call our chief applications engineer. He works with a lot of our customers on these complex challenges that are related to different environments for our sensors, as well as the different instrumentation options and making sure that they fit properly into the right environment for your testing needs. So what we're going to do is we're going to cover a series of topics today. We're going to start off with some basic standard digital protocols and get into some of the field bus protocol definitions. We're going to move into some configuration considerations and show you some interesting ways in which you can connect sensors in different environments. We'll talk about sensors and instrumentation examples. There's many, but these are just a few examples that we'll show you on the versatility working within different communication networks. We'll talk about some of the trends, best practices, and a little bit on the applications examples that show you the versatility again. We'll save time for Q&A, so be sure to use your meeting chat feature for any questions that you might have. We'll try to address those throughout the event. So to kick things off, again, thanks for joining us. Keith, it's all to you.
Hi, everybody, and thank you for joining. First, I'd just like to talk about sort of standard analog versus digital protocols. Analog protocols have been around forever. Load cells inherently have a millivolt per volt output. Very typically, the signal from load cell can be connected directly into some kind of a data acquisition system, or with an inline signal conditioner or internal amplification in the load cell signal can be converted, amplified up to a higher level signal, like a plus or minus 10 volts or 4 to 20 milliamps. Those signals then can be input into various systems, data acquisition, PLCs, controllers. That is still by far the most common method used today. It's a lot of it very legacy. It has some advantages. It's high speed, can be very high accuracy. It has advantages. Digital systems, though, have advantages as well. And so we're seeing more and more people wanting to, say, convert to digital and then run a digital network or into a digital system versus straight analog. So advancing to digital output, digital installation costs are often lower cost environments for sensors. For example, you have a load cell and you have a converter, or I should say called a signal conditioner, to go from, say, millivolts per volts to milliamps. And now you have to have an input card to go from milliamps to digital in your network. Well, what if you just convert to digitally at the load cell and now connect directly to the network? So it can have fewer costs. Cabling can be less expensive too. Load cell cabling should be shielded, high quality cable. Some network cabling can be quite a bit less expensive. Can be more scalable when you're digital. You can add more sensors. You don't have to necessarily add any more channels or anything into your system. It's just adding another node or another item into the existing network. In digital connections, a lot of times you can swap sensors and things with really no interruption. You don't have to rescale or do anything that may be sort of inherent in the sensor. The calibration or the digital data is already scaled, and you can just swap in, and the sensor outputs pounds, for example. Multiple sensors can be daisy chained. So say you have a RS-45 or any number of different kinds of network runs, you can chain sensors together. So you can have one cable, say, going out and coming back, and all the sensors are, say, hanging off that pair. So that can be quite convenient. Again, built-in error detection with digital output. Sometimes the A to Ds can say sense if a bridge is open or something wrong. So instead of having to go and do troubleshooting, the network may tell you, okay, that sensor has a problem. Again, can be more accurate. Once this signal is digitized, there are no further conversion errors. There may be latency or delays as things get converted digitally, but once it's digitized, if it's 100 pounds, it's going to be 100 pounds anywhere else that digital signal goes. And if you have, say, a long cable run with low level millivolts per volt, or even 4 to 20 milliamps, there can be noise introduced into the signal. So if it's digitized right at the sensor, usually the longer the cable run, the more option or more opportunity for noise to be introduced. So if you digitize right at the sensor, right very close to the bridge, there's less opportunity for noise. And then once it's digitized, noise no longer causes, say, errors or measurement issues. It's more noise might cause disruption. You might not get the signal, but if you do get it, it should be correct. So it's not like you have a drift in the signal due to noise, like you might see in an analog system. Next slide, please. So there's a bunch of different communication protocols. Analog, obviously, USB, say connected to a PC over a virtual serial port. That's super common, very commonly used in test and measurement data acquisition. In RS-45, RS-232 have been around for a long time. There are a lot of instrumentation that may have serial ports that they can connect it to a PC. Maybe you have to use, say, a serial to USB converter, because most computers don't have serial ports anymore. A lot of times, too, newer instruments will have USB ports, but those really just act like serial ports. So the PC connects to it as if it were a serial port. Modbus RTU is basically Modbus over RS-45. It's also Modbus TCP, which is over the, say, standard Ethernet protocol. Got CAN bus, CAN open, DeviceNet, CC link, Profibus, Profinet, Ethernet, TCP IP, Ethernet IP, EtherCAT, EtherCAT power over EtherCAT, and you got PowerCAT, Circos, and the list goes on. One thing to be careful of is many of these protocols sound similar, so you might think they are compatible. For example, Ethernet, TCP IP, and Ethernet IP. Hey, those sound pretty much the same. Turns out they are completely incompatible in that if you buy, say, an Ethernet IP device, it's not going to work on your Ethernet TCP IP network or vice versa. Certainly, it could be made to work with converters and things, but they're not natively compatible with each other. Same thing with various Ethernets and EtherCATs and EtherCAT-P. They aren't the same, and they would connect differently. Same thing with Modbus, RTU for TCP, different. We have a list here of various protocols. Again, 45 we talked about, pretty common. It has some limitations, but it's widely used. A lot of like PLCs and things may have RS-45 serial ports. Analog, and you can always connect analog signals into networks, and that's usually done with some kind of a analog card. So it might have 6, or not 6, usually it's 4 8 channels of, say, 4 to 20 milliamps, and then you have a sensor that connects via that module into a network. We got CAN open, DeviceNet. There's no one protocol that really is correct or right. And the answer typically is what is the existing network, right? So you don't say, oh, I'm going to use DeviceNet. Usually it's you're using, some controller that uses DeviceNet, and now that dictates that your other devices want to be DeviceNet. Next slide, we have some other protocols. Again, some of them may be used by certain manufacturers. Allen Bradley may, commonly use Ethernet IP, or Siemens may use a different protocol. Again, it's not necessarily one is right or wrong. A lot of times the network exists, and the answer is for your sensors, you just want to connect them into an existing network. Of course, if you're starting from scratch, usually you don't start with a sensor and say, build a network around the sensors protocol. You would decide on a protocol and then pick the appropriate sensor to interact with your network choice. Next slide. Even more options. Again, like I said, if you're going to pick one, say you're going to go digital, like something like RS-45 ASCII or something would be quite easy to use. Certain ones are pretty easy for anybody, and some of them require, say, an expert. So, if you have an Ethernet IP network, you need people who actually know how to program and, set things up on that network. Next slide. Configuration considerations. So it's pretty complicated if you think about all the different protocols. But again, if you simplify it, what protocol is already in existence? A lot of times that's really the answer. You're trying to connect to something that's already on a network or an existing network, or connect devices together. They already have certain protocols. And you don't really get a choice necessarily of which ones to use. So you have to identify the protocol. So that's an important step. What is the existing protocol? Say the protocol used to transmit data from load cells to the data acquisition system should be compatible with the other equipment in the test environment. And so also distance between the load cell and the instrumentation is key. Some protocols aren't great when you have, say, very long cable runs. But if it's existing network, you may not have any choice, but you could maybe convert or do something instead of just connecting straight into the network. Say control systems, CAN bus can offer robustness against electrical noise, and something like Ethernet TCP IP offers very high bandwidth. That's like your typical intranet connection, right? So it offers very high bandwidth. Again, communication protocols should be selected based on the specific requirements of the application. Some protocols may require additional hardware. In response rates, predictability, flexibility, remote accessibility, all determine what protocol might be more desirable. In accuracy and precision, a lot of times in test environments, accuracy is quite important. Say precision and resolution important. And so in a high precision test environment, like a laboratory or a calibration facility, load cells with high accuracy and precision are normally essential. In contrast, say in an industrial environment, say a production line, that may not be the main consideration, but maybe durability, reliability, or say robustness of the protocol may be the driving factor. In a communication protocol used to transmit data from the load cell to the data acquisition system can also affect the accuracy and precision. Some protocols, such as Ethernet, offer high data rates and low latency, which can improve accuracy and precision. Say others may have lower data rates and higher latency, which can degrade accuracy and precision. For example, if you say it's a pressing operation and you're looking for like peak press forces, if the say the data throughput is too slow, you may not actually be capturing the high values. And so that would be a serious accuracy problem. You say your peaks are, X and they're really 2X. So again, if you have, or say the resolution isn't there, you're trying to do a very precise operation. If the network or the protocol can't support the resolution required, it may be impossible to achieve the task. In application resolution, capacity and range of the load cells should be selected based on the maximum load that will be applied in the test environment. And so you really need to select a sensor with a capacity that's slightly higher than the maximum expected load to allow for some margin of error. It is important, not necessarily network specific, but it's important to think about, what is the maximum load, especially if it's in sort of an industrial environment where you have, say, the risk of downtime is very high. Or the cost of downtime is very high. So what is the maximum expected load? And then what's the maximum expected accidental load? What if somebody hits an emergency stop or, emergency shutdown or something jams up? And then you want to size the sensor to be bigger than that so it doesn't get destroyed. And that is very important. Should also have spares on hand if there is the possibility of damage. The communication protocol should be able to handle the data rate and resolution required for the load cell's capacity and range. So again, if you pick a sensor and a resolution and a capacity that you need, if the sensor is connected to a network, they say that limits the bit resolution or the data rate, that may be a problem. So those are things that should be considered. Next slide. So environment. The environmental conditions in the test environment, such as temperature, humidity, and vibration, can affect the performance of the load cell. And so basically, you need to select a load cell that is rated for the specific environment, and that includes whatever signal conditioning may be attached or connected to the load cell. And the communication protocol should be robust enough to handle the environmental conditions in the test environment. So sometimes, say, there may be high levels of electromagnetic interference. Certain protocols will be better suited to reject that noise than others. Another thing too, in temperature, say tests that have, say, extreme temperature ranges, sometimes the load cells can be rated for very extreme temperature ranges. The digital instrumentation that may be attached to them may be the limiting factor. So say you have an inline or say integrated amplifier, that amplifier may have, say, a smaller allowable temperature range than the load cell. So that can be okay if it's still within the requirement, or it might be necessary to say locate the actual amplifier outside of the test chamber, for example, and then say digitize outside of the oven or outside of the freezer or whatever. So those things to keep in mind. Some examples here are just, basically how do you connect a sensor into a system? And the most common still is analog connection of the sensor into some type of data acquisition system. Here we show our model BX8, which is an 8-channel device that can accept millivolts per volt, milliamps, volts, can accept encoder inputs, whatnot. So basically all the sensors would be wired to something like this, and then this would be connected to a PC and running data acquisition software. Potentially these boxes could be networked, or you could have access, say, remotely via a network, but basically hardwired to a device that's connected to a PC. Again, these are used very commonly in lab, robots, test cells, all kinds of things where you kind of have a sort of a small scale implementation. These can be the most accurate and some of the best solutions in many cases. Moving on, you have digital integration into, say, an existing PLC. In this case, I use an example of our wireless tension link. It doesn't have to be wireless, obviously, but once the signal is digitized at the load cell, it happens, in this case, to be broadcast digitally and received by a wireless gateway. And that gateway has certain protocols available, RS-45, Modbus, or ASCII. And so attaching it to, say, a PLC with a digital input that accepts RS-45 would be a good solution. Again, why wouldn't you just connect, say, via the analog inputs on something like the PLC? Well, you may not have any analog inputs, or they may already be in use. Typically, there's not an infinite number. There may be 2, 4, 8 analog inputs. They may already be in use. Whereas digitally connecting sensors to the existing PLC, you can possibly connect multiple sensors to the same, say, serial port on the PLC. So it's pretty common to do this, and very common to have, say, adding sensors into an existing system where the PLC was selected, originally when there were only 2 sensors. Now they want to add some more sensors. The inputs aren't available, but a digital connection can be used. Next slide. So here we have trying to, say, connect a sensor into an existing network, and there's a number of products that could be used for this. In this case, we're showing our model INF1, which is a DIN rail mount inline signal conditioner, and it comes in a variety of different field buses. So basically, you hook the load cell via its millivolt per volt output up to a ADC input on the INF1, and then the INF1 has a connection to the existing network, and that could be Profinet, Ethernet IP, Ethernet, TCP IP, EtherCAT, all different kinds of protocols. And so this would be an easy way to connect into an existing system. Next slide. So this would talk about a network that maybe we don't have the appropriate converter, or depending what hardware you have, it just may not be that hardware in, when you say hardware, load cell or sensor, you may not have that sensor available, and there may not be a directly connected device available for that sensor that can convert to the network protocol. So what we can do in this case, we can broadcast wirelessly, digitally to a gateway. And then the gateway is connected to what's called an Anybus converter. And Anybus is a brand. There are other brands available. Anybus is a good one. And that basically converts the RS-45 Modbus to whatever protocol the network may be running. So again, Ethernet IP, Profinet, they're available in a lot of different versions. Again, this wouldn't have to be wireless. We could have, say we had an Ethernet connection and you want to use an Anybus to convert it over to Profinet. Or say we use our INF1 to convert to, some protocol, and then there's something else in the network that's running on another protocol, you use an Anybus converter. So these are really handy. When we say we sell a system, if we know the network, we can actually set up our end of it so that our stuff is talking to the Anybus converter. And then, of course, it'd be customers' requirement to set up the other side, which is the communication with the Anybus into their network. Next slide. So this is an example, say, of multiple sensors hooked up into a network. There are various devices that could take, say, analog signals, convert them to some type of a network connection. In this case, showing our model BX8, which can have up to 8 sensors hooked up to it. Also has a couple encoder channels, so you have up to 10 sensor channels. And these are available with either EtherCAT or CAN bus, or has a UAT port that could be used, say, with an AnyBus converter to convert to any number of other networks. This could be connected to the network, and then you could also have any number of these boxes connected into the network. So you could scale it by adding more boxes. But this would be a way to say analog sensors into a network. And this is, say, useful for when you have existing infrastructure, maybe a lot of channels. Something like this may make a lot more sense than buying, say, individual input channels for, say, 4 to 20 million to the network. Next slide. IO-Link is interesting. IO-Link is like a digital sensor data protocol. And so it's not network specific, it's actually network agnostic, but it's a digital data protocol. And there exist any number of different hubs that are IO-Link hubs. And the other side of the hub goes to the network. So you can have an Ethernet IP to IO-Link hub. You can have a Profinet to IO-Link hub. You can have any number of different networks are available, or say network hubs are available to go from a specific network to IO-Link. And so what IO-Link does is a digital data protocol. It basically allows sensors to be attached into a network. It standardizes the connection. It's a standard protocol, standard cabling. IO-Link sensors use low-cost, industry standard cabling. They're all interchangeable, so it'd be an M12 connector on each end. And if you don't have special cabling, IO-Link uses a 24-volt differential signal for the data, which is very noise immune, so it's very good in industrial environments. You can hot swap sensors. There's some health and condition monitoring built in, so it's really nice, actually, nice way to integrate sensors into an existing network. Next slide. We're talking a little bit about instrumentation options when you're talking about trying to connect sensors into networks. So first off, what types of sensors are we talking about? It's a wide number of sensors. Industrial environments, a lot of times lifting and shackles and things are used. In test environments, our low profile load cells might use torque sensors, might be miniature sensors. Miniature sensors typically don't have amplifiers integrated inside them because they're too small, so they might want to use an inline module of some sort. But this is an example of different types of sensors that may want to be integrated. Next slide. Specifically, our low profile load cell, our 1200 series, and also our other 1100 or even 1000 series low profiles are available with wireless digital modules attached to them. And what this does, it takes the load cell data, digitizes it, and broadcasts it wirelessly. And then that wireless data can now be received by any number of devices in the wireless ecosystem. Also can be converted and say connected externally into other networks. Next slide. So we have IO-Link specific load cells. These are load cells, low profile load cells with IO-Link amplifiers built in. These have the M12 4-pin industry standard IO-Link connector. These have all the advantages of our low profile load cells, and then they're easy to connect into any network via one of the IO-Link hubs I mentioned earlier. We can also do inline modules. So any load cell, doesn't matter if it were the size of your fingernail, could be connected, say, via an IO-Link amp or a digital converter via an inline module. And we show our CSD up top, which is an inline amplifier inside of a stainless steel IP-rated enclosure. We also have connectorized versions. Again, we talked about IO-Link using standardized connectors. So maybe you want to have M12 connectors on the module, so it's all kind of plug and play. These are just some examples. Again, we can do RS-45, Modbus, CAN bus, CAN open, ASCII. We can do IO-Link, number of other protocols available depending on the module. Next slide. And wireless isn't network specific, but it's digital. And once the data is digital, it can be converted and transmitted into other networks. Also, we've seen a wide interest in wireless sort of uptick in the interest. It's not just for kind of exotic applications. Basically, a lot of times cabling is an irritant, people tripping over cables or having to run cabling. So wireless can be nice just because it eliminates some of the cabling. Give this example of a wireless load pin that's transmitting data. Next slide. So we're talking about wireless communication or wireless systems. We have a sort of an ecosystem of components that are all intercompatible. And the nice thing about this digital wireless is once it's broadcast, you can listen to it just like in your car. You have 6 people or 1,000 people listening to the same radio station. You can have any number of things listening to the digital data that's being broadcast. You have a handheld display. You could have a converter that converts to an analog signal, say to go to a PLC. You have a converter that converts to an RS-45 stream to go to a different device. We have digital displays. You have big scoreboard displays that can all be, say, connected. There are modules connected to the PC for data logging, or say somebody wants to write their own code to interact. You can use that, say, via PC interface module. So lots of options and all very versatile. Next slide. So I mentioned our INF1 earlier. This is an example of an INF1 single sensor digital signal conditioner. And then there's also the INF4, which has 4 inputs. So it can be used with 2, 3, or 4 sensors. It could also be used with 1 sensor, but really no reason to use a 4-channel one. You only have 1 sensor. So what these do is they take the millivolt per volt input from the sensor and they convert to digital. And then that digital data is basically available over whichever network you select. And these are all specific. So you don't have one model that does PowerLink, can open EtherCAT, Profinet. And sometimes there's a kind of a tax to be paid to the various vendors who say control Profinet or whatever. And so you definitely don't want all of that built into one because it makes the cost go way up. So each one very specifically is either the Profinet one or the Profibus one or the Modbus one, et cetera. They also always have an RS-45 connected because some of the programming is best done via PC, and that'd be over a 45 connection to the PC, maybe with a PC USB to INF converter. And you can do certain things over the PC, then the other, the digital data is basically transmitted to the network over the field bus. The 4-channel ones are interesting. They are typically intended for like scales and things for weighing applications where the sum of the channels is required. And so it'll do some diagnostics and things. It'll tell you if one sensor is bad or, useful in that way, but it doesn't necessarily let you easily look at each individual channel, because it wants to sum them up, and what's available over the field bus is the sum of the total, all the channels. However, it is possible to get the individual A to D counts for each channel. And so we have a number of customers who actually do want to look at each channel individually. Say with a 3-axis sensor, you want to have each axis hooked up to a different channel. And in this case, you could have raw scaling that can be pulled over the field bus. And that might be, say, 2 million counts equals 2 millivolts per volt. And then in the processing, you could apply the scaling factor and convert to engineering units. So that's certainly possible. A number of customers doing that. But just keep that in mind. The 4-channel ones, if you want like pounds coming out of it, it's going to be a sum of the 4. These can have remote.
I was going to just say Mark has a question about the INF1 and INF4, as well as the same question for the IO-Link, and that is, what is the latency and or response time typically as seen in the PLC? So what is the minimum response time as an example?
Yeah, that's a very good question, and it can be a limitation. These INFs, they sample at 600 samples per second, so certainly not going to be any faster than that. And then there's some latency. Typically, it's on the order of a couple of milliseconds for the INF1. And then the IO-Link, 200 samples per second. And I think that's about a 50 millisecond latency on those. So they're great for certain things. Terrible and not going to work for other things. If you're saying sort of impulse testing or something, they're going to be way too slow. So good question. I think that's about it for these. These are pretty nice. We've been selling a lot of them And it's kind of interesting. You say, which one's the most popular network? Turns out none of them. The mix is pretty wide across all the available protocols. These are a couple of newer instruments. The black box is an EtherCAT T amplifier, so power over EtherCAT, has a 4-pin M8 connector on it, and that's a 6-channel device, 16-bit. It also has a USB port, so you can hook up a PC. We have PC software that comes with it, so you can do data logging and data acquisition. But if you also want to hook up into an EtherCAT network, like say for robots or something, this is a great device for that. And it's commonly used with our 6-axis, multi-axis sensors. And then the box up in the upper right is similar architecture. Internally, it's still 16-bit, 6-channel, but it, instead of EtherCAT and USB, it has Ethernet TCP/IP and CAN bus, and has a UART port, and it comes with a UART to USB converter, so that can be plugged into a PC as well. So again, different protocols for different applications. Not one necessarily better than the other, just depending what network you're trying to connect to. Next slide. A gateway device. I mentioned this. This is a little bit of a zoom in on this device. This is a wireless gateway. It takes any of our wireless digital data streams and would convert that into RS-45, Modbus, or ASCII serial output. And why ASCII? Well, if you're going to write your own code, ASCII can be quite easy. You know, I could almost do it. Some of these other protocols, you need a pretty serious programmer to tackle it. But then these, say the Modbus RTUs, or I'm sorry, Modbus RS-45 is commonly used like with like PLCs and things. So it could be easy to connect this into an existing network that has a serial port. Next slide. This is our model BX8. It comes in this HD15 variant, which has 15 individual, or I'm sorry, 8 individual 15-pin connectors for hooking up sensors. These can either be Ethernet TCP/IP, which would be like, you know, through a standard router hooked up to your PC or whatever your local network might be. You also have EtherCAT options, and this isn't power over EtherCAT because these boxes end up plugging into power, but it's EtherCAT. And then CAN bus, CAN open options as well. These also have UART ports, which can be used, say, with converters to go to other different types of networks. These are nice, 24-bit, 48,000 samples per second per channel, and the samples are synchronous, so all the channels are clocked and sampling at 48,000 samples per second. And if you have multiples of these boxes, they can all be synchronized together, so they're all sampling synchronously. And these include graphing and logging software and configuration software. You know, if something's on a network and you want to say use it over EtherCAT, it's nice to have the ability to actually configure it via its own software. And then the device on the network is just say outputting data, or, you know, using basic commands over the network. Now, sure, you know, there's lots of different commands available, but keep things simple, right? If you're just looking for data, you don't need to be able to program it over your network connection. So a lot of that is better done, say, with PC software. Next slide. So staying ahead of the communication curve. Talk a little bit about trends in the industry. IO-Link is definitely a trend. It's coming on strong. It offers a lot of advantages. I like to think of it a bit like 4 to 20 milliamps, but digital version. So it's not, you know, specific to a network. You have to have input, say, modules or hubs that take the IO-Link and connect them to a network. But because it's digital, it offers a lot of advantages, you know, error correction or error detection. You can have uptime monitoring, you know, how many cycles has the load cell seen. A lot of that is available in the IO-Link protocol. It's compatible with a wide range of sensors. We can basically connect IO-Link modules to any millivolt per volt output sensor. It can also be connected to voltage output sensors. It can be built in depending on the sensor. Can certainly be in inline modules. In IO-Link, cabling is, you know, industry standard M12 cabling, so very cost effective. Again, it's 24-volt differential, so it's very noise immune, so you don't need, like, you know, twisted pairs, you know, heavy shielding, any of that kind of stuff. It'll work pretty well on most any cabling. Next slide. industrial IoT protocols, protocols that facilitate seamless integration and data exchange between various devices, systems in both industrial and lab settings. Basically, can enable remote monitoring and control, data analytics, improve efficiency and productivity. So as factories get more and more integrated into, online systems where you have management and things can get reports and see uptime and, various things that can be monitored in real time in a production setting. Again, the traditional divide between IT, information technology, and operation technology networks is blurring. So this requires communication protocols that can bridge the gap and enable seamless data flow between the two domains. So test and measurement data flows into the IT realm. Next slide. Number 3, wireless protocol. So wireless technologies have certainly improved. Very high speed. Wi-Fi 6 is relatively short distance, but very high bandwidth. And Bluetooth 5 is much improved, than earlier Bluetooth protocols. And again, 5G can get very high bandwidth cellular data. And, they're getting more reliable and faster. And so more and more of that being integrated into industrial environments. So it's particularly useful for embedding sensors in automated manufacturing, aerospace, automotive testing, real-time industrial machines, robotics, enabling untethered movement and data collection. So a lot of things are possible with wireless data that wasn't so easy when done with wired solutions. Next slide. So increasing adoption of time-sensitive networking, and TSN provides deterministic and synchronized communication over standard Ethernet networks, like EtherCAT, for example, provides synchronization. There's crucial for real-time control and coordination in robotics and for ensuring precise timing in things like calibration labs if timing is important. Secure connectivity, the growing number of connected devices, security is becoming paramount. Secure communication protocols with encryption and authentication features are vital for protecting sensitive data and preventing unauthorized access, especially in secure calibration labs or secure military environments, for example. So there's a lot of options available. Some of our wireless, for example, can be encrypted and locked down.
Yeah, Keith, there's another question about which wireless protocols do your products use and what security settings are available.
So the WTS products use 2.4 gigahertz, so basically standard Wi-Fi. They have, and typically it's not at all encrypted. It is a proprietary protocol, so it's not so easy to interpret, but certainly easy if somebody were to buy the right equipment. But there's a feature that can be enabled that adds encryption, and so it encrypts the data. So it's not only over the proprietary format, but it's encrypted within that format. And then you got to be careful you don't lose the encryption codes. Next slide. So best practices, tips, and key considerations. So does the sensor or instrument natively support the desired communication protocol? Probably not, but sometimes you can buy a sensor that actually has the protocol built in. If not, what are the available options for protocol conversion? Be gateways, converters, some things we've talked about previously. Will protocol conversion introduce any latency or data loss that could affect the application? Maybe, yeah, absolutely. There may be latency. Some protocols, you just lose data. And so you might lose packets of data, and a packet might have multiple data points in it, right? So that could be a real problem. Some protocols have, say retransmit, or they have, checksums and things, and, basically, ways to ensure that data gets through. Some don't. How will each sensor or instrument be uniquely identified on the network? Consideration, different protocols use different ways of doing that. You may have to hard code things in, or sensors may say identify themselves to the network. Things like IO-Link, they basically plug in and start broadcasting their data in already engineering units, for example. What configuration parameters are required for each device to communicate effectively baud rate, data format, communication protocol. If things aren't set up right, you hook them up, they don't talk. And sometimes it's not going to be super obvious. It just isn't working, right? And so it must be understood, what configuration items or what is available, how much configuration is possible. Some sensors may not have a lot of configuration, so you have to do all the configuration, say on the network side. Sometimes you have to match configuration between the sensor and the converter and the network. So just need to understand what you're dealing with. How will the network configuration be managed and maintained? Is there a centralized configuration server, manual configuration? Again, do you have somebody who's an expert and willing and able to work on this? Example, like say you buy a bunch of Ethernet IP stuff and you don't know that much about Ethernet IP yourself. You better have somebody on staff who does, right? And again, it's not really prudent to say rely on the manufacturer to help, because typically sensor manufacturers aren't network experts. So you really do need somebody who knows the network well to set up the network side of things. What data format does a sensor instrument output? Some may output raw counts. We actually talked about it earlier, where some of our amplifiers can give you raw counts over multiple channels. Sometimes it will be scaled in engineering units. Some of our IR-Link actually outputs at percent, so like 100%, 100.00%, 99.2%, and that would be converted downstream from a percent to engineering units like newtons or pounds. Sometimes there's data packets that are encoded. And if a packet gets lost, does it retransmit, or is it just lost forever? Things like that to consider. Next slide. How will the data be interpreted and processed by the receiving system? Are there any scaling factors, calibration values, or data transformations that need to be applied? If so, how is that done? Do you have somebody who knows how to say, get in and make configuration changes in the network to add scaling factors and things? Because that would be done potentially, say, on the receiving side, not on the transmitting side. Does the application require synchronized data acquisition from multiple sensors? Say you're doing a force displacement measurement, may be important, especially how fast that measurement is happening, or how fast the event is happening. Say it's like pushing something together quickly. You want to know the force and displacement. Those two things may need to be synchronized together. So certain protocols are terrible at that, and some of them would clock and lock those two measurements in time. So it's important to consider. What security measures are in place? Is there authentication, encryption, access control? Can anybody get in and start messing with settings, or is it locked down so that only certain people have access? How will data integrity be ensured during transmission? Intermission checksums, error correction, error detection, and some retransmits if, say, something doesn't get through. Other different variables there. And then, are there any regulatory or compliance requirements related to data security and privacy? Potentially like a military installation. It might be that you're just not allowed to use some of these protocols. Some of these things may have, say, rewritable memory in them. So that means that's actually not allowed in and out of the secure areas. So again, when we talking about digital, there are certain considerations that don't necessarily apply to analog devices. Next slide. So communication protocol tips. You define the required data rate and bandwidth. Again, certain protocols, certain signal conditioners have serious limitations on their bandwidth. Some of them are quite fast. Some of them may be only in the hundreds of samples per second, or maybe even slower than that. And that's perfectly fine if you're monitoring, say, the weight of a tank. If you're doing some kind of a force feedback operation, it may be entirely too slow. In the distance requirements, some protocols are much better for very long distances than others. So you're using a network that really doesn't work well over long distances, and maybe there need to be some conversions in between. Use some protocol that is more suited to longer distances, and then convert later versus right at the sensor. Noise and interference. Industrial environments can be a lot of electromagnetic interference, shielded cables, error detection devices, correction mechanisms. Some protocols are inherently resistant to noise. Those are all key considerations. One thing to notice too, sometimes there can be a lot of noise, and when you put the sensor in, that's like the thing that notices, or you notice it because you get weird measurements, and they say, it's a sensor. a problem with the sensor. Not necessarily. The sensor is just the only thing in your network that is sensitive enough to that it's obvious. So, a lot of times it's really not, you say, a defect or a problem in the sensor. It's showing that there's, say, serious noise problems that need to be addressed. And it might be they're having bandwidth problems too that you didn't realize, and the noise is, affecting that as well. So tracking down the noise and mitigating it, or using protocols that are more inherently insensitive to it, may be in order. Next slide. So data speed and output. Again, some applications demand predictable and guaranteed message delivery times, or say you have multiple channels, they may need to be synchronous. You don't want just each channel kind of randomly delivering its data, missing data from some channels, getting multiple readings from other channels. So you might need real-time control. Again, if it's like a force feedback or a robot control or something, it might be very important for everything to be clocked together and have very known latencies and tight control on timing. In existing infrastructure, there may be compatibility constraints. If legacy equipment or specific hardware is already in place, the communication protocol must be compatible. So upgrading existing systems to support a new protocol can be costly and time consuming. So it may sound like a good idea, but may not really be viable in the end to upgrade everything. So you have to assess compatibility with the existing infrastructure, and that greatly simplifies the integration if you understand what you're dealing with and then work within those bounds. Next slide. So certain best practices. Again, if timing is important, you should prioritize timing protocols. Load cells and force measurement devices often operate in critical applications where timely and predictable data transmission is paramount. So you choose protocols that match your requirements for accuracy and timing, such as real time for synchronized force measurements, particularly dynamic or control-oriented systems. Implement error detection and correction. Force measurements are susceptible to noise and interference, potentially leading to inaccurate readings. So should utilize protocols that incorporate robust error detection and correction mechanisms to safeguard data integrity, especially in harsh industrial environments where electrical noise or signal degradation is prevalent. And consider bandwidth and data rates. Load cells can generate data at varying frequencies depending on the application. The application requires a high-speed measurement. Then you got to make sure that everything, the protocols, the signal conditioning, converters, everything support that rate. If you have any bottlenecks, you're going to choke it and maybe get large errors due to missing data or just not capturing it correctly in the first place due to, say, too low of a sampling rate at the ADC conversion. Moving on. So here's a few applications where we aren't talking about like straight analog data anymore. Animatronics is pretty interesting. There's lots of robots that are used in say entertainment and those kind of things in the theaters. Those are pretty cool in that there's a lot of work being done to make them look very realistic. So they have force and torque feedback in the joints. Initially, what they'll be doing is say taking data, so you have the item go through a motion and then take say force or torque feedback and kind of log that and analyze it and look and see what's happening. Might be that the joint creates torque spikes, which show up as torque spikes, but also show up as say jerky movement or not as realistic as possible. So say analyzing the data allows for better control algorithms to be created. This is an example of our MRTP miniature reaction torque sensor, which is integrated into a joint, and then that is hooked up to a BX8 to data logging software that comes with the BX8. So again, let's look at time versus torque in the joint. Also could be measuring, say, position of the joint, and then decide, if they can make changes to the algorithms to make for a smoother motion or a more realistic motion. Next slide. This is a hover lift. Pretty interesting. And a lot of these things would be hardwired. Maybe a scale might be attached to the trolley or a scale head or a display. But a lot of times, actually, you want to log data and get into a PC. So instead of somebody sitting there hand keying it, just wirelessly transmit to a PC that's say sitting at the the desk or whatever, and then its digital data could be broadcast say to a wireless receiver and then it can be logged and recorded. And just like might look at a patient every day when you move them. Are they getting heavier? Are they getting lighter? Certain things like that are monitored in real time, or, on demand in hospitals and rehab facilities. Next slide. This is an application of, say, an automated test for end-of-line testing of the medical devices, happen to be syringes. So we have our model SMT, overload protected load cell, in line with the syringe. Basically, an operator would load the syringe in. Kind of a boring job. Load the syringe in, hit go, and the system will automatically, push and pull on the syringe. There's a certain, say, window of allowable forces. If it's too hard or too easy, right, that's a fail. And then the data from the load cell is hooked up through a CSD inline signal conditioner with Modbus output. That's to a PLC. And the PLC basically has some limit switches. And so if the force is within the desired window, you get a green light. If it's outside of the desired windows, you get a red light. The operator, the green light, he moves it into the good bin. If it's red, he throws it in the reject bin. Very common in industry for these type of tests to take place. Next slide. So, customer challenge was to monitor the press force in a metal forming plant. And so there would be a bunch of these presses, and customer opted for IO-Link load cells. And the IO-Link load cells allowed them to easily connect to their existing Ethernet IP network. Basically, initially, they were going to use 4 to 20 milliamp output load cells. So load cells with basically 4 to 20 milliamp signal conditioners built into them. And then they were going to have 4 to 20 milliamp input. I don't call them cards or, devices that connected to their Ethernet IP network. And those network interface devices were rather expensive, actually. And so instead of using 4 to 20 milliamp amplifiers, we swapped IO-Link amplifiers. And then, basically there's a wash as far as the signal conditioning goes on the load cell, but now you have an IO-Link signal, and then that can be easily connected to these IO-Link to Ethernet IP hubs that are readily available. And so they were able to add, a lot of channels relatively inexpensively into the network by going to IO-Link. Next slide. This is a robot application. Lots of robot stuff going on these days, so we like to talk about it. But this is a pretty simple approach where somebody has a little pincher and they wanted to add load cells into the pincher to measure the grip force and do some force feedback control so the robot wouldn't clamp too hard on items that are being picked up. So this incorporated our convex BT miniature load button load cells, one on each side of the pincher behind some little gripper things. And then the two load cells were connected through an INF4, and the sum of the result was available over EtherCAT into the robot controller. So they can do force feedback as part of the robot control program using this setup. And we're now on to the question and answer session.
This is great, Keith. If you have any questions for him, use the chat feature. We'll be here for a couple more minutes to answer any questions that you might have. One thing that you had mentioned, Keith, is that we can do a system calibration, system configuration if you're buying multiple components, but it's important for us to understand when you're buying those instruments and sensors to understand what network you're trying to fit them into prior, correct?
Yes, and say sometimes it's important to know the specifics, exactly what you need from us so that it integrates seamlessly.
Has there been any protocol that you found has not worked with any of the devices that we offer? Or are we able to find something compatible?
We haven't ran into any yet. These are all like kind of known working devices in that they're pretty standard. And so like the Ethernet IP or the Profinet hardware has been well vetted. And so really, when they don't work, it's really probably because there's some trouble on the network side. In some cases, the guys we're dealing with aren't really network people. So it turns out they may not have a good network guy, or maybe they're an integrator and they're going in and maybe they don't have access to the network guys. And so it's typically problems communicating between the network and the device, not problem with the device itself.
That makes sense. Marcus has got a great question. How far away from having many of these common digital interfaces built into the sensors and not needing an external box? How close are we to that?
We're not too terribly far. Some of them could be built in today. Some of the devices are relatively larger and would have to be miniaturized. Again, the little miniature sensors have fewer options. Bigger sensors, you basically put a box on the side and put the amplifier inside of that. And we do a lot of that. We do a lot of the digital protocols that way today. Good question.
Great question. Again, if you have any more questions, please use the chat feature. And we've got a couple more minutes left. Keith, we see a lot of applications that want to use remote accessibility to data. They're put in the field. Maybe we see these traveling sensor kits that people take to different locations. What have you found that has been helpful in putting together the right instrumentation that can work in those types of remote locations?
Yeah, it's interesting. There's a lot of different ways to do it. We do have options like for cellular network connectivity, or connecting into, say, the Ethernet. You connect to a PC that then's connected to the internet, and that could be, access all over the world, for example. So we do have customers doing that today, and we have worked with them. One of the challenges is sometimes if you're trying to drop something into a network that then communicate outside of that network, you're dealing with the sort of the rules of your IT people who probably don't allow that. And so, you say, oh, this thing connect out to the outside world. Yeah, except the firewalls and all that don't allow it. And your IT guy basically is never going to allow it. So there are ways to get around that. Again, cellular, that basically bypasses the local network. That's typically better, though, for data dumps versus continuous, real-time monitoring. Again, there are ways you can set up things so they can only communicate out and not take any communications in, or you can set it up so when it boots up, it establishes like a secure connection, kind of like a VPN or something, where it connects outward, but it doesn't allow really any incoming connections except very well controlled. So again, there are some challenges, but it's quite interesting and becoming more and more prevalent.
That's great information. Well, I can see we're coming to the end. We don't have any more questions here, but if you do have questions, of course, we have representatives and distributors throughout the world that are ready to work with you to ensure that you get the right sensor and instrument from Interface. We have tens of thousands of options and certainly can work with you to ensure that it fits your environment. Again, if you have any questions, please reach out to us, reach out to our representatives and our distributors. The last thing I'd like to say, Keith, is that thank you for a very informative webinar. If you are looking for Interface on why to choose us, well, we've been doing this for a long time, 56 years and counting. And we build a lot of standard products that are available in our 35,000 product catalog, but we also do a lot of customization and we can do a lot of system configuration. So let us know how we can help you to meet your exact specifications. We do design our load cells for precision. Accuracy is important. That's why accuracy was a point in this conversation. We can customize our products and we can build to spec, especially when you have an OEM type solution where you're looking to put a sensor into a robotic arm or you're looking to use it in a medical device or something along that lines. We also can work with our engineers and our manufacturing team to help get the right solutions together. So if you have any questions, you can always reach us on our website or reach out to us here. We'll be posting this presentation online on our YouTube channel. Be sure to stay tuned. We'll keep you informed of new products and opportunities. And Keith, again, valuable information, a very hot topic right now. These webinars are produced based on demand of questions, so glad you were able to put this together. Thank you so much.
My pleasure. Enjoy it.
Thanks, everyone.
Thank you.